So I'm going to do a couple questions from this, then I'm going to decide if you guys want to see more from a section or less from a section. We can sort of figure that out, trying to time out this review session to go for about 2 hours. And our first topic is related rates. And I decided to start with question number 2. It's a question with similar triangles. So a light is on the ground 20 meters from a building. Here we go. We've got a man 2 meters tall walks from the light directly towards the building at 1 meters per second. And how fast is the length of his shadow on the building changing when he is 14 meters from the building? So I'm actually going to redraw this a little bit. We've got our light, we've got our building, and we've got our man that's 2 meters tall, so I'll label that again. And what's happening is the man is walking towards the building. So this is going in this direction. What we have to label on here are the things that are changing and the things that are staying the same. So if I call this my x, then my x is increasing. And as that increases, the shadow on the wall, which I'm going to call y, is going to change as well. We also know that this is a fixed length of 20 meters from the light to the wall. So everything that can change with respect to time, we can write as a derivative, or dx dt. We know that that is increasing at 1 meters per second, so we can write that as a positive value. dy dt is what we're asked to find out. How fast is the length of his shadow changing? So we want to find dy dt exactly when he is 14 meters from the building. So if this is 14 meters here, at that moment, does it make sense that we're trying to find it when x is 6? Because we labeled the x as the other part. So what this is telling us, and this is the thing in all exponential functions, is that the x value is a function of t, and the y value is a function of t. And that's going to become important when we find the derivatives of this equation, because it involves using the chain rule. Now, in every related rate question, we have to somehow make an equation that connects the rates that are changing. So we have our x and we have our y. This one is a similar triangle question. Do you see that this little purple triangle right here is similar to this big green triangle right here? And so there's many ways that you can set up similar triangle kind of ratios. One way we could do here is that the small length on the purple triangle compared to, sorry, I'll call it the base. Does that make sense? If I call the bottom there, the base on the purple triangle compared to the base on the green triangle has to be the same ratio, because they're similar triangles, as the height on the purple triangle compared to the height on the green triangle. That's one way we could set up our ratios. Sometimes people also like to just look at like a tangent ratio. Can you see on the purple one, the tangent ratio is opposite over adjacent, 2 over x. And on the green one, that tangent ratio would be y over 20. I can rearrange this on here with the first equation. I multiplied both sides and got xy equals 40. Can you see my blue equation? If I multiply both sides by x and both sides by 20, I get the same equation. So in similar triangles, you might see a different relationship to make your ratios the same, but either way will be fine. I sometimes really like thinking of the tangent ratio, because it's like, that makes sense to me that opposite over adjacent has to be the same for this one as it does for the other one. But in similar triangles, however much you have to times 2 by to get y would be the same you'd have to multiply x by to get 20, so there's a common ratio between those values as well. Once we have our equation with x's and y's, now we can take the derivative with respect to time of both sides. On this side with the xy, you would have a product rule. Keep one the same, derivative of the other one. And because both x and y are functions of time, when we take the derivative with respect to time of something like y, we do the derivative like normal, like what's the derivative of y? It's just 1. But then we always have to write the chain rule, which would say you'd also have dy dt as a result. Same thing, now we keep the y the same and I take the derivative of the x. Well, derivative of x is 1, but then because of the chain rule, I'd have a dx dt. So every variable, because they're a function of time, when you take the derivative, those rates of change appear. And now we want to find the specifics. Yeah, just do it. We want to find the specifics for when x was 6, and when x is 6, we can find out exactly what y would be. In fact, here we've got our situation that based on this, y would have to be 20 over 3 at that moment, right? Because if x is 6, you just take this equation right here, xy equals 40. If x is 6, the only thing that makes sense for y to keep and make 40 is if you had 40 over 6, which reduces to 20 over 3. Plug in everything you know, the only thing you have left to solve for is the dy dt, and you get your value. And it's a word problem, not bad to have a sentence in the end. Make sure you include your units. Negative 10 over 9 meters per second. Yeah, I can move up a little bit.
Thank you.
Just a couple of notes about related rate questions. So, you set up your equation, but x is changing, y is changing. Those variables have to stay. If there's something that doesn't change, you can put that number in. So be careful with, and I think I wrote it in red here, that 14 in red is not something set in place. That's only, you're going to only use the values that, like when x equals 6, you're going to only use that once you've done your derivatives, put everything in, and now want to find a specific moment. So the danger in a related rate is you plug in the specific moment too soon, and then when you do the derivative, it just like disappears, and then you're like, what? Where did everything go? Where do I plug things in? Because things will disappear. If you put 6 in for x, and I do the derivative of that side, it's just going to be 0. I want to point out something with the first example, but not do the whole first example. So I'm going to go back to the first example, because it's related to what I just said there. So I have a picture. A plane is flying towards a radar station at a constant height of 6 meters above the ground. If the distance between the plane and the radar station is decreasing, at a rate of 400 kilometers per hour when s equals 10, what is the horizontal speed of the plane? So in this question, the s, they might have given a diagram, I had to redraw it here, but the s is the distance between the plane and the radar station. You've got a horizontal distance x and a vertical distance y. Now this vertical distance y, I labeled it as y on here, but it is a fixed rate because it's always 6. So it would have been okay to label y as 6 here. However, if I think that each of those are functions of time, since y is fixed, does it make sense that dy dt would be 0? It's never changing. So I could either have this as 6, and then y doesn't even come into the equation, or I could leave y in the equation and then have dy dt equal to 0. The ds dt was decreasing at a rate, so the decreasing makes sure that we have negative 400. And we're trying to find the horizontal speed of the plane, dx dt. And here, we've got a squared plus b squared equals c squared. Okay? This could have been right here. This could have been 36, because it's fixed. If it was 36 and I took the derivative with respect to time, this would have been 0. But keeping the y, when you plug in dy dt as 0, can you see that it would result in the same thing? So you sort of have different options there. If you put a variable in that's not changing, but keep it in there, you're going to have your dy dt equals 0 and have it go away. Me personally, when a number is fixed, I like to just put that fixed number in there because it's going to make, like, this isn't hard, 2y dy dt, but it's sure a lot easier just to write a 0 right away. And then from here, we're going to be plugging in things, right? We want to find the specific time when it's 10. So this is 10, this is 6, that makes this a squared plus b squared equals c squared, that makes that 8. That's our specific moment. So you have your one where things are changing, and then you look at the specific moment. And once you have the specific moment, that's when you plug things in. And from there, why I shouldn't, no, may as well just show it all because we're so close to being done. You see that we get a negative here? Does it make sense that a negative is because it's going like to the left in the diagram that we drew? And it also shows up as negative because you're getting closer to the station. There's going to be a moment where it's right above the station, and then after that, it's going to be positive again because you're going to be getting further away. All right, I did want to go over question 3. A conical cup is 4 centimeters across and 6 centimeters deep, and water leaks out the bottom at a rate of 2 centimeters cubed per second. How fast is the water level dropping when the height is 3 centimeters? So draw a picture. We've got a cone with a height here of h and a radius here of r. What do we know? We know that this is actually 6. Just a little typo here. That, oh no, the diameter is 6. So that's fine. The diameter is 6. diameter is not 6. This is the height. Height is 6. The diameter is 4. Radius is 2. So this should be an H, right? H is 6. Radius is 2. We're told that dV dt is -2, which is telling us that volume is a function of time, and we want to find dH dt, also telling us that your height is a function of time. Those are important because that it means that we can do our chain rule when we set up our equation. We need to know our formulas. So if you get a conical question, do you remember the volume of a cone? 1/3 pi r squared h. Which technically, right, it also means that the radius is a function of time. Does it make sense? As you go down, the height is changing and your radius is getting smaller. The problem is it doesn't tell us anything about dr dt. So in these cone questions, we use similar triangles again, and we use the tangent ratio, because do you see that when I take this here, my radius and my height, it makes a triangle. And as that height is going down, this angle right here is exactly the same. It hasn't changed anything as it goes down that cone. So those are similar triangles. And because they're similar triangles, the ratio of the radius divided by the height always has to be 2 divided by 6. Because my big one, the radius is 2, and my height is 6. That would be my tan ratio. So that tan ratio stays the same as we go along. Because it stays the same, that allows me to rearrange that and get the r by itself, which is nice because then I can go back to my equation and substitute in. And now my volume equation only involves height. This is going to be way easier to take the derivative, because if you took the derivative with the r in there, you would have to do product rule, and you'd have to include dr dt, and we don't have dr dt, so that's problematic. So by using the similar triangles, we can take dH dt of this side and dH dt, not dH dt, just ddt, take the derivative with respect to time on both sides. Derivative with respect to volume, that'll just be dV dt. With the h, you bring the 3 out in front, subtract 1 from the exponent, and then the chain rule would have the dH dt afterwards. Now we wanted to find when the height, so now when the height is 3, the radius would be 1, doesn't matter what the radius is though, we just need to plug in our values. We knew that dV dt was -2. We can plug in 3 now for the height. Rearrange our equation. Include our units. I almost feel like they might be fussy in the way that I have the final sentence written. Because dropping at a negative, would that not mean going up? Like, I think they might be nice. Because you've got the negative in your answer to show that your height is decreasing. But technically, you wouldn't need the negative there because you have the word dropping. Sorry. You can move over so that you're not in the JR Pillar perspective. Okay, I want to do 7 and 9. So we're going to go to 7 next. I probably chose 7 because these are questions that I have a personal non-preference for. I don't love these questions. So I don't love them. Somebody else probably doesn't. They're probably good for reading. AP seems to love having particles travel on the x-axis. It's like a particle holiday that they just love going along the x-axis. So here we've got a particle traveling along the x-axis, and we've got its equation, where x is in meters and t is in minutes. At what time is it furthest to the left? Okay? So if that's its position, then the derivative, right, we've got that SPA, the derivative of its position is velocity. And if we solve the velocity, we know that at time equals 3, the velocity is 0. The reason I can X out the time equals -2 is we're only worried about between 0 and 4, what it's going to be. When is it the farthest to the left? This is an extreme value theorem question. And so, we check the endpoints at 0, where is it? At 4, where is it? And at where it changes direction, where is it? And so it's the farthest to the left at time equals 0. Because it's starting at 1, then it moves to the right until it gets to 28. At 28 it switches direction, and it starts coming back, and at time equals 4 it's back to 22, but the furthest left it ever was at its starting position. So for a particle moving along the x-axis, it's like having a graph going up and down, but maximums are where you're furthest to the right, minimums are where you're furthest to the left. But it's just kind of flipping that to thinking about it moving along the x-axis. At the same time, on the same interval, what is the particle's maximum speed? So we're going to look at our acceleration. We're going to set that equal to 0 at time equals 1/2. And now we're thinking of an extreme value theorem for our velocity. At the endpoints of our velocity starts at a velocity of 12. Then it changes at 1/2. And at 1/2 it's at 12.5. And at 4 it's at -12. Particle's maximum speed is 12.5. Where would we have to be careful in a question like this? Okay, with the speed, be careful in a question like this and I've seen this on old IB questions, I'm just going to make up numbers as if these are the actual numbers for our question. But let's say I was doing a different question and I did my calculations and I got 12 and 12.5 and negative 14. Can you see yourself tempted to say the maximum speed is 12.5 again because it's the biggest number? But in this situation, what's the answer? The 14, right? Because speed is the absolute value of velocity. You see the minus 14 and you go, oh, that's really small, but it's actually a speed of 14. We have to be careful with that. So I just wanted to point that out in that situation. You especially see that, okay, you have to be careful with, let's say this is my velocity graph, right? And they ask you for the maximum speed. Most students will say this, and that's not the right answer. The maximum speed could also be this, because if we did speed as the absolute value, I'll absolute value this graph, that's higher when I take that absolute value. But in the moment, you see the word maximum, you have a graph, you just think about that high value. Just something to be aware of. And yeah, that one wasn't, I know it was in the related rates section. I don't know how it snuck in there. It wasn't really related rates, but it was a good thinking question to come up with, so I wanted to do that one. And I wanted to do number 9. What is the radius of a soda can with a volume of 512 cubic inches that will use the minimum material? So again, this isn't really related rates, this is more max min optimize. Oh yeah, that's, the title says optimization as well. So this is more of an optimization question. Volume of a cylinder is pi r squared h, and the surface area of a cylinder is 2 pi r squared plus 2 pi r h. So if this was an exam question, this is an example of, they've decided that they don't want to mark a whole bunch of questions with students making up wrong formulas and working with them, which is very possible, because they don't give you a formula sheet. So they're like, how about we give you the formulas just to make our life easier? So we know you don't use any wrong ones. So, we want a minimum surface area. It's an optimization point. What are we given? We're given a volume, and what that volume does is it allows us to rearrange our equation so we can either get h by itself or r by itself. Because right now, our surface area formula has both r and h, which makes it difficult to do the derivative of, because then we would have, you know, complicated chain rules. But if we replace the h with 512 over pi r squared and do a little bit of simplification, then we get an equation that's just in terms of r. And if it's just in terms of r, we can take the derivative and set that derivative equal to 0, and then solve. Now, if you have that r squared on the bottom, I would move it over, then you can multiply both sides by the r squared to get that variable out of the bottom of your equation. Then you can cube root both sides. Write your answer to 3 decimal places.